Hello, everybody. It's really great to see so many of you back here. We're really excited to be kicking off our workshop series for the future of Blockchain University Hackathon. Firstly, it's great to see you all yesterday at the launch event. I hope this was really helpful for you and has kind of planted a seed and got you thinking about some projects that you might be able to build. For any of you who did miss the event, we have posted all the links to the recordings in our Discord channel and in the Hacker Pack. So once this workshop kicks off, I'll drop all of the links to those in the chat, so you should be able to access those properly. As we mentioned yesterday, these two links are super important. They're a really great way for you to keep in touch with all the communications for this hackathon. So if you make a note of those two links, that would be really great. I'm really excited to announce that we have Mehdi here to join us today to provide his workshop on an introduction to rollups and Arbitrum. I will just invite Mehdi to the stage now, but before we kick off, I'd love to also tell you about the Arbitrum Ambassador Scheme. It's a really great opportunity for you all to get involved. Everybody in this call has the opportunity to join Arbitrum's University Fleet, where you will lead virtual and in-person events. You can create your own content, and it's just really great for you to grow your own personal network. So again, I will drop this link in the chat soon after we kick off, and feel free to take a look at that in your own time. I'm sure it's something Mehdi might also discuss in his chat, but that would be really great to hear more about that. And any questions throughout, please do use the question channel, and we will ask Mehdi those in the Q&A at the end of the session. So without further ado, I don't want to take any more of your time, so I'd love to invite Mehdi to the stage to kick off our workshops.
Great. Hello, everybody. I'm Mehdi Salehi. I'm integration engineer at Off-Chain Labs, and we're going to discuss about like an introduction on rollups and Arbitrum. Can you confirm you can see my screen?
I think you're good to go.
Great. So let's not waste time and jump into the workshop. So as we discussed, like today, I'll give presentation about like an introduction to rollups and Arbitrum. And it's good to like start with Ethereum and like see why we need to choose like another chains on top of Ethereum, and what are the limitations on Ethereum. So like the main, if we want to like put it on some words, the main limitation that brought us to like have rollups or other layer 2s or other solutions is that, like, you know, we have limited space and resources on Ethereum. Like almost each 12 seconds we have a block, and on that block at most like we can have 30 million gas, but like the target is 50 million. Like if any block reaches like more than 50 million, then the base fee would be increased, and like it would be like more expensive to use the chain. So like in general, there are two issues with Ethereum. One of them is number of transactions are limited, or like better to say, the computational and storage limits on the like per second is limited. And also like that would be so expensive based on demand, which you see like if any event happened, then like the gas spike and it would be so expensive to use. So what are the alternatives and solutions to have cheaper network and cheaper transactions with some more amount of throughput of transaction and TPS? Like for sure, like the first answer comes to mind was alt L1s, like another blockchain, another layer one blockchains like Ethereum, but you know, having different model to scale more than Ethereum. But in most cases, if I don't want to like to use like all cases, they sacrifice the security and decentrality for scalability. So that's why, like, money goes through Ethereum because it's the safest, most decentralized blockchain that covers smart contracts. The other way to do scalability is on-chain scalability, and like the main way to do that is sharding. But like it needs more time to reach to the point to use sharding, and also it's not enough by itself to like scale to like billion users. So it brought up us to like this point to use off-chain scalability, and there are different ways like to have off-chain scalability. And the first one of them, like we which like proposed like right after Ethereum, like even before Ethereum on Bitcoin network, was sidechain. And like in sidechain, you have a bridge that like you can move assets between main chain and side chains, and like the side chain is completely another blockchain. Uh, so like in the side chain, you need to keep the data, like, and also like there should be some people to like uh, uh bring into consensus that like the state on side chain is okay. So this is another like thing that is not good about sidechains. So the other one is Validium, and like Validium is very similar to ZK rollups, which I will briefly talk about ZK rollups in this talk. But the problem with Validium is very similar to sidechain. Like you need to keep uh, data of the other chain. Like before, like rollups, the solution that was like people think that okay, this is the solution that we can get into and use it for uh, like scalability on Ethereum is plasma chains. And plasma chains is very similar to what we have as optimistic rollup these days. But the problem was like the data availability. Like we could like find out like if like the state on the other chain is faulty. We could do that, but the problem was there should be some parties to keep the data of the other chain, and like if they uh, like just shut down their PC, then like all people were right. So it brings us to a better way to like do off-chain scalability and use Ethereum as security layer. So there are three main ways to do that. For now, like the first one is state channels. Like state channels is like when two parties create like uh, multi-wallet uh, kind of a smart contract, and then do all the other things off chain. And based on what I described, like state channels and like most of them are payment channels even, are so limited. Like it's not doable to do like all the things that you can do with Ethereum on state channels. And also there are lots of other problems which I don't want to get into it, because like the three main ones that I want to discuss today is sidechain, optimistic rollup, and uh, ZK rollups. So let's start with rollups. What are rollups? And like to describe rollups, I want to start with sidechains. So like as I explained before, side chains are like separate blockchains. Like they have their own consensus model and like their own database. Everything is separate from the other chain, other than having a bridge, like by which, with this bridge actually people can bring or like bring out money from and to the main blockchain. So what is important, so important here, is this two-way peg. So what do we mean with two-way peg is like, for example, if you bridge like one Ethereum to the other chain, we should be sure that like there is one Ethereum locked in this blockchain and exactly one Ethereum on the other chain. Otherwise, like, in one part, like people will rot. Like, um, if anything happen on the side chain, like to have more ETH than what people has on bridge, then like people like the first people bridging back to the blockchain can just like deplete the bridge, and like there would be some others that are locked on the side chain. So the main issue of side chains is this two-way peg. And like to assure and guarantee this two-way peg, like there are three questions, what to be assured and who and how can assure that like this two-way peg would be like guaranteed. And the main question is like what. So to be sure that we have two-way peg, we should have these two. The first one is, we should have uh, data availability on the other chain. Um, by data availability, I mean, like the side chain is, as I said, like very similar to the other blockchains. So it has its own database. And like, for example, on Ethereum or like blockchains like Ethereum, um, validators and also like miners will keep like the blockchain database, and all node runners will keep that as well. So like, in Ethereum blockchain, like all node runners and especially like the validators have a copy of that data. But like on the side chain, like, the Ethereum chain validators won't keep anything of that chain. So like, um, based on the type of the side chain, like some people may save that data, but the problem is like, um, that set of, like data availability committee would be not large enough, and like if they lose that data, then um, it's hard to like it's not doable to like have this spec. Like you cannot breach back because you don't have data of that side chain. So this is the first like requirement of having these two-way peg, and the other one is correctness of state transition on the other chain. Like like it's another separate blockchain, right? So it's very similar to Ethereum. Like based on transactions that come to the sidechain, the state of that sidechain would be changed. And what is important there is like, the validity of that transactions, and also like the validity of the uh, state that is changed based on those transactions. So like, if we don't have such a validity, then like anyone or like the people who are responsible to keep these sidechains can create their own fake transaction, steal all the money based on the state, and use that like, breach to deplete funds from L1 blockchain. So uh, to sum up these two, like first of all, we need a way for like other parties to have the data available about the chain, and also they should like they or some parties should be able to use that data and checks if the all like transitions happened on the sidechain is correct, and if not they should be able to enforce that faulty. uh, so rollups try to answer these two challenges. Like the main challenges we're dealing with on rollups and like any layer two is the these two questions, like data availability and state transition like integrity. If we reach to the point that like we are guaranteed about these two, we can say we have a like great layer two. But there is another thing which we should have it, and this is censorship resistance. Like in the side chain that I showed you, like as I said, like there would be some parties that validate this blockchain, and like it could be very similar to Ethereum, like proof of stake validators. So if they censor you, then you cannot work with that system. So like censorship resistance in the other one, that like uh, if we want to claim that like the our layer two has security almost equal to Ethereum, we need censorship resistance as well. So there wouldn't be any party that has some strong power over us, because we can no one can censor us. We can send transaction, the state will be changed, data is available out there. Anyone or some parties can grab that data, change the like change state, and if anything is wrong there, they can like enforce the integrity of that state transition, so everything would be great, right? So the first one, the first trait that we should have on layer 2 roll-ups is data availability. And as I said, like to check the correctness of transition state, uh, first of all, you need the data, right? You need to have the data available uh, to check, like in the future, to check like if the estates that are proposed are correct or not. So, like here we have two different ways to keep, the data. Um, in optimistic rollups, we keep transaction data, like we keep some version of all transactions on L2 back to like somewhere. It could be L1 or other databases. So it can be like transaction, or on the ZK rollups we use state differences. Like they did, we keep the result, like what storage changes would happen based on those transactions. So like based on the uh, layer two, that type that we're using, we can use different data, but the main thing that is important is like to have data available for others to check the correctness of transition state. So the second and like very important question here is like where to put data to be assured that you know in the future all people would be uh, assured that they have access to that data, like and like the first and the best like solution that comes to mind is rolling up. By rolling up we mean rolling up all the transactions and send them back to Ethereum L1, or like the underlying L1 chain. So this is why we call roll up because for data availability, we decided to get the transactions and roll them up and on the uh, put them back on the L1 Ethereum chain. So like we have two different chains on Arbitrum. I will discuss it at the end, but Arbitrum one is roll up, but we have another chain which is not rolled up. We call them any trust chain, and the name is Arbitrum Nova. And like on Arbitrum Nova, the only difference between these two, Arbitrum One and Nova, or like rollup or any trust, is that like in Arbitrum Nova, we don't put the rollup transactions back to L1 because it's more expensive. We have data availability committee to keep that data. So like I just explained it here to just let you know that we call roll up because we in roll-ups we put a fingerprint of the transactions back to L1. But there are other cases like this that we keep like we don't post like the fingerprint of transaction to the underlying chain. Validium is the other one. Like in Validium solution, we don't send the the data, the transactions or like any kind of data back to L1. But like validity, a Validium committee would keep those data. And for sure, like rollups are so like more secure than the other ways of keeping data because like the committee is a limited set of people who keeps the data, but uh, like in rollup, like any any person can just run their own node and like get the data. So as I said, like anyone can use Ethereum mainnet, collect all past data, and create new estates based on that transactions. Like you have all the transactions of L2 on L1, so anyone can run Ethereum node, grab that transactions and check new states based on those transactions. So we have data availability on rollups like that. But what about state transition integrity? Now that we have the data, anyone can check new states. But who can enforce the correct state if it's faulty? Like like if the state on L2 is faulty, like having a faulty transaction or like just setting some faulty uh, outcome, like who can enforce that faulty assertion and assert it, or like how to enforce it? The state transition integrity means that like to be sure that based on the transactions that are rolled up on Ethereum, there should be some parties that can check the data and see if like anything is faulty and enforce the right one, the correct one. And here we get to the point that like we have two different type of roll-ups based on the way that we enforce integrity. Uh, an optimistic roll-up we have fraud proofs, and on ZK roll-ups we have ZK validity proofs and system to be like to ensure that uh, and guarantee the state transition has integrity and it's correct. I won't go through ZK rollups today because our talk is focused on optimistic rollup and Ethereum. So, what is optimistic rollup? And why optimistic? So we know that what are rollups, and what rollups should have, like the main two one, data availability and state integrity, and also censorship resistance. But why we call optimistic rollup optimistic? It's because, like L2 chain can forward create new states without Ethereum validation. And like Ethereum L1 wouldn't validate anything on the L2 chain. So what happens if like any faulty state proposed is that one honest party can dispute it in the future. So it's kind of optimistic. Like we are optimistically, uh, like continue working with the chain, and we are optimistic that like validators in this chain act correctly. And if anything goes wrong, then like uh, one honest party can find the issue and propose the issue, and correct that you know um, that like state integrity issue. So it's optimistic. But how to challenge? Um, we have data on chain. Anyone can compute new state based on those like transactions on L1, and they can find the faulty one if it happens. And then what? There should be, like because we want to like have the security as it is on Ethereum. There should be a way on Ethereum that if someone find a faulty, state on L2, there should be a way to like, prove that like who is wrong, who is um, and who is correct about like the new state, and also there should be a way to enforce it. So based on that, we need two other things on Ethereum. First of all, we need some L2 state checkpoints on Ethereum chain, and also we need a way on chain to judge the right state. Like why do we need L2 state checkpoints on Ethereum? Is like, if you find a faulty, state, then there should be some checkpoints on the mainnet, so that like a judge on Ethereum can judge if you are right or the validator is right. So we need some checkpoints to dispute based on that. And also, like these checkpoints, validators will post checkpoints back to Ethereum. I will discuss it on Arbitrum side of the presentation in more detail, but validator will put like some checkpoints of the L2 state back to L1. And other than that, we need a way on chain to judge right state. So we have set of contracts for rollups that can judge the conflict. Like if uh, any honest party found a faulty state, like based on the states, like checkpoints that validators put on L1, if like the disputer find any faulty one, there are set of contracts which we in Arbitrum we call them one-step proof and challenge system, which that party can go through, use those checkpoints and prove that like that checkpoint is not correct based on the transactions that are that we have on L1. So we have transactions, we can we have checkpoints, and an honest party can dispute the system using some smart contracts and logic on Ethereum chain to prove that uh, the outcome that is posted by validators are not correct. So let's jump into Arbitrum. As you know, Arbitrum 1 is optimistic rollup, and why its optimistic rollup is definitely we post rollup transactions back to Ethereum main chain. So we have data availability because like you can go to the like you can run your Ethereum node and you know check like two smart contracts we have like the inbox and sequencer inbox. Check those contracts and see like the all the roll up transactions on Ethereum that is sent by Arbitrum. So you have the data on some specific addresses on Ethereum for Arbitrum, and this is data availability, right? Because you have transactions there. And also it's great to say that like we like the Arbitrum one is the only optimistic rollup that has active fraud proof system. Like uh, we are the only optimistic rollup that has set of smart contracts that an honest party can use them to judge the states that are posted by validators. um, so we have state integrity as well, and also we have censorship resistance as well, which I will discuss in the next. So let's jump in to like Arbitrum and see what's inside Arbitrum. Um, First of all, as I said, we have data availability, but how we have this data availability is through sequencer. So sequencer is a party, is it like agent that receives transaction from you. So whenever you send L2 transaction to a node, that node will forward it to the sequencer. It will receive transactions, then order all incoming messages, and then publish them uh, like through transaction back to all Arbitrum nodes. And also, as we discussed, like batch transaction and compress them, or like this part is rolling it up, rolling it up and send them back to Ethereum mainnet. Um, in one word, sequencer is transaction ordering service. Let's like show you some uh, figures that like makes more sense that what's going on. Whenever you send transactions on L2 on Arbitrum 1, our like the Arbitrum sequencer will receive it and order the transaction. As I said, it also uses like a feed, sequencer feed, to tell like Arbitrum nodes that this is the ordered transactions I want to put on Ethereum mainnet. So this is soft guarantee, like just sequencer, um, you know, assure that like it will send transaction based on this order. But like because it's a roll up, it will batch and compress them, or like better to say roll up the transaction and put them back to L1 Ethereum chain. This is what the sequencer is doing. Like this is the only thing that sequencer is doing. Like receiving transaction, ordering them, and send them back to L1, and also update notes that about that order transaction. This is the only thing that sequencer is doing. And it's about data availability, right? Like now we have data availability here because we sent roll up transaction on L1 chain. Uh, and as I said, like through this feed, like this sequencer feed, and also checking with L1 chain as well, Arbitrum nodes see the ordered transaction. Like whenever they receive like ordered transaction, they will use their state transition function, um, like which is uh, like coded on Arbitrum Nitro node, it will use that like state transition function, like or Arbitrum client, to change the state based on those transactions and create L2 blocks. This part is very similar to Ethereum. Like in Ethereum, like we have Ethereum node, not Arbitrum node, and also like we have Ethereum client which changed the state based on transaction to create L1 blocks. But here, like just names are different, and like Arbitrum nodes are very similar to Ethereum. We use Geth as the underlying base software. We fork Geth with minimal changes to have Arbitrum nodes, which handles one of the things that is handling is state transition function. So to sum up from the first point to here, we receive transaction like from sequencer. Sequencer will use sequencer feed to like connect to Arbitrum nodes and tell them about order transaction. It will also roll up the transaction and send them back to L1 chain. Arbitrum node will receive transactions from sequencer feed instantly. They will just like create new state, like based on state transition function, and create L2 blocks. One small like hint, and it, like it's good to know about it, is like Arbitrum nodes will use like sequencer feed to create new states, but they will check L1 chain as well. And whenever a new batch of transaction is finalized on Ethereum, they will check with the one that sequencer sent them. If it's like the same, it will go through. Otherwise, it will change the state, like the L2 blocks. It will rework. So like it's safe. Like Arbitrum nodes won't just rely on sequencer and what it proposed, but also like on L1 chains as well. So like from first to this point, we talked about data availability. But what about state integrity? Like how can we be ensured that these L2 blocks are correct, like these state changes are correct? And here we have another party uh, other than sequencer named validators. And we have two main type of validators. The first one is active validator, and the second one is defensive validators. So active validators, as like it comes from their names, like they are actively compute the transition state based on the transactions that are on Ethereum L1, like the roll up, transaction. It won't listen to sequencer. It just see the L1 contracts, see the ordered transaction on mainnet, on Ethereum mainnet that is posted by sequencer. When they are finalized, it will compute the transition state and put some checkpoints back to L1. So like they will they will put some checkpoints and a stake on that, showing that they have some skin in the game. uh, and if something falsy happen, we have defensive validator, which are sit and listening to all new checkpoints, and also like all incoming transactions that are roll up to Ethereum L1. And if any frauds happen, defensive validator will start a challenge and use one step proof system to enforce the correct state to the system. Like the more completed version of the graph would be like that. So like we send transaction to sequencer, there is a sequencer feed like updates Ethereum nodes. also like it will send batches back to L1. And so like um, active validators will use L1 chain to have this, like set of ordered transaction, and use state transition function to check the state, change the state, having L2 blocks, and put some checkpoints, as I said, like back to L1. So like what is important here is like we have, transactions on L1 chain, and we have some checkpoints. uh, this opens up the opportunity for us to, challenge, like in the future. And as I said, defensive validator would do that. Like they will check like L1 chain for batched and compressed transaction here. Like they decompress that, you know batches of transactions, and have the order that are settled on L1 chain, and compute, like this part they have it as well. Like they compute L2 blocks for themselves, and check for the checkpoints that are, sent by active validators. And if, it sees like any differences between what it expects and what it is settled, then, they will jump into the challenge and dispute, and use smart contract set, we named one step proof, and using our challenge system to challenge that specific checkpoint. And like it's doable. Why? Because as I said, we have transactions on chain, and also, we have the checkpoints. So based on like the our system, they can, you know uh, find like the part of state changes that is faulty. Uh, and at the end, the loser of this challenge would lose their stake, and the other one would be rewarded on half of that stake. So we assure the integrity of the system. But what is important here is, like because we're optimistically uh, get forward on the chain, we don't have, we should have enough time for validators to see, and check all new, checkpoints that are proposed by active validators. And they should have enough time to check it, find it, and go into um, a challenge period, like a challenge with that active validators. And at the end, win, like if the checkpoints are incorrect. So we need a time there to be sure uh, about all these things, and we call it dispute period. So like the state that is sent to L1 is not final um, on rollups, on optimistic rollups, because like L1 chain don't know about anything about, the state transitions happen. It has transactions on L1, it has checkpoints, but like L1 chain for sure, it shouldn't, do all these state transitions. Uh, Otherwise, we don't need rollup. So if anything faulty happens on that specific part, like L1 chain would um, be like, and the smart contracts on the L1 chain will handle and judge the challenge between defensive and that faulty active validators. And like so these checkpoints like won't be finalized before dispute period, which is currently 1 week. And like the reason behind that 1 week is that like it proposed by Vitalik. So after 1 week, if No, none of like decent defensive validators challenge that block, that checkpoint. It will be finalized, and the state is final. So it needs a week to have finality. And as the latest thing I want to discuss a bit about censorship resistance as well. I showed you like we have data availability and also state integrity. But what about censorship resistance? By censorship resistance, I mean like if sequencer, like in this model that I described, if sequencer decided to censor you, or uh, do whatever you want, like delay your messages or anything like that, like then you would be censored. Like suppose that you send some money to L2, and sequencer decided to not let you get them back on L1, then you're completely censored. But on Arbitrum we have a model named force inclusion, which you as a user can send L2 transactions directly on L1 chain, not going through sequencer and like this batch and compress thing here. So you will put your transaction, like L2 transaction data, on L1 chain, and after a while you can force include it. By force inclusion, I mean like force inclusion on the ordered transactions that Arbitrum node and also validator would use. So even sequencer cannot censor you, and for sure validators can't do that as well, because if they change like the state, then defensive validators based on the transaction on L1 chain can dispute it. So no one can censor you on Arbitrum 1. And yeah, that's it. There are lots of things to discuss, but because of limitation on time, I think it's good to call it there.
Mehdi, thank you so much. That was really, really interesting. It was great to see all of your graphics, which I hope help everyone kind of understand a bit more about the technology. We have about 10 minutes left, so I wondered if I could quickly run through some of the questions which have been dropped into the chat. So the first one we had was when you were mentioning utilizing sidechains, and you said a good solution to achieve off-chain scalability. I wondered if you could just discuss some of the other applications and benefits which can be achieved through using sidechains.
Yeah, sure. Like actually, sidechains are very similar to other chains. Like for example, like Polygon is not completely sidechain. We call it commit chains because it puts some like data back to L1, but it's very similar to sidechains. They have their own chain, like they have their own set of proof of stake validators, and it is so cheaper than Ethereum. No, so like it could be another whole chain, like general EVM compatible chain, or it can be even app chains. Like you can create your side chain, and to run just your app on that chain. But the issue is like it was like all this that people think about sidechain, because that there would be a huge responsibility there to run the other sidechain and make it secure enough for people to like breach their asset there. So people will go with roll up these days, because they don't need to have any consensus model on the other chain. They just need to have like sequencer and the validator, which is fine.
Very much. Another question we had from the chat was for the sequencer feed, and you mentioned how it provides a soft guarantee. There was just a question around what this soft guarantee is and how it perhaps differs from an absolute guarantee.
Yeah, that's a great question. Actually, like as I said, whenever people send transaction to sequencer, it will create something we call incoming messages. Like it will say that okay, these transactions would be in a block, and like order all the transaction based on that. Uh, Whenever like just when receiving transaction, it will create that order transactions like list and would send it through the feed to all different Arbitrum nodes. So Arbitrum nodes are listening to that WebSocket, sequencer feed, and whenever they receive a transaction from that, they will compute, the state based on that. In the first hand, like Arbitrum nodes would trust the sequencer feed. But what if like sequencer puts some other data back to L1? It may just like tell you that I will put this order of transaction and then put another ones, and that's why Arbitrum nodes listening to Ethereum L1 as well, and see like what are like the batch that are posted by sequencer to L1. So if like it is difference between these two, it like all Arbitrum nodes would reorg to the uh, correct one. And like it's good to give you that numbers as well. Like on Arbitrum, we almost like each 1 or 2 minute we have a batch posted on Ethereum. And on Ethereum, like it takes 10 to 15 minutes to be finalized, So like it would take like at most 20 minutes to have the data posted by sequencer on L1. And like after that 20 minutes, it will check, like Arbitrum nodes check the L1 finalized order transaction. And if it is the same, then it's hard finality, not soft finality.
Thank you so much. I think we maybe have time for one more question. So obviously, the fact that this is the Future of Blockchain University Hackathon, I wondered if you could perhaps provide any tips for people or students who are looking to get into the Web3 industry.
Yeah, that's a great question as well. Actually, like it's good to find, trends before, like all people know that trend. For example, right now, like not all people, but there are lots of people that started talking about L3s, like app chains, this kind of stuff. Like it would be great to like be in crypto Twitter, be on um like listening to podcasts to find these trends. And I gave you one of them now. Like we have Arbitrum Orbit to run your L3 chain, and there are other alternatives as well. And teams are very eager to find out what are they, how you can work with them, what creativity you can have on those trends. By trends, I don't mean like buying selling cryptocurrency for sure. Like I mean finding the new tech that is coming, like, and right now it's L3s. So yeah, this is like general thing I can say. And other than that, like I think we have enough resources, more than enough resources to find things out. But if you have time to track all of them.
Thank you so much for that. I wonder if perhaps whilst we're and finishing up, whether you'd be happy to share some of your socials, so if people have any questions or anything like that, maybe you could drop a link in the chat just for anyone who's looking to reach out. But yeah, for everyone who's attended, thank you so much. I think I speak for us all when I say thank you to Mehdi for a really interesting workshop. We're back tomorrow at the same time. We're taking it back to basics with our part 1 Solidity workshop. So that should be a really great one. And I'd love if you could all attend that one too. But yeah, without further ado, Mehdi, thank you so much. Really great to see everybody. Great to see your insightful questions. And I look forward to seeing you all again tomorrow. So bye-bye. Thank you.